Two Theorems on Conics by S. Lefschetz. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Two Theorems on Conics by S. Lefschetz. 1. This paper contains two unrelated theorems on conics, of which the first is virtually contained in a proposition given by Poncelet, while the second is the equivalent for conics of a well-known theorem on rational quartics, and so far as we know is new under this form. To both propositions we apply considerations of number of projective conditions satisfied by a given configuration. 2. The first theorem is the following. When two complete quadrilaterals circumscribed to a conic have a common diagonal, their vertices, not situated on the latter, are on another conic. Let O, A, B be the triangle of reference, and S equal to x squared minus yz equal to 0, the equation of a conic S tangent to O A and O B in A and B. The two tangents drawn from the point a, situated at 0, 1, and lambda, are simultaneously represented by 4 lambda times the quantity x squared minus yz plus the quantity lambda y plus z squared equal to 0, which can be written 4 lambda x squared minus the quantity lambda y minus z squared equal to 0. By changing lambda into mu, we obtain the tangents drawn from the point b situated at 0, 1, mu, so that 4 lambda x squared minus the quantity lambda y minus z squared plus the expression 4 mu x squared minus the quantity mu y minus z, the quantity squared, the expression times a constant kappa equal to 0, called equation 1, represents a conic going through the intersections of the two pairs of tangents. Similarly, a conic going through the points of intersection of the tangent from the point A prime situated at 0, 1, and lambda prime with the tangents from the point B prime at 0, 1, mu prime will be represented by 4 lambda prime x squared minus the quantity lambda prime y minus z, the quantity squared, plus the expression 4 mu prime x squared minus the quantity mu prime y minus z, that squared. That expression times a constant kappa prime equal to 0, called equation 2. And we must show that for proper values of kappa and kappa prime, the equations 1 and 2 will represent the same curve. Such values will satisfy the system. The fraction lambda plus kappa mu over lambda prime plus kappa prime mu prime equals the fraction lambda squared plus kappa mu squared over lambda prime squared plus kappa prime mu prime squared equals the fraction 1 plus kappa over 1 plus kappa prime, which effectively can be solved for kappa and kappa prime. Thus we get kappa equals negative the fraction, the quantities lambda minus lambda prime times lambda minus mu prime over the quantities mu minus lambda prime times mu minus mu prime. And substituting in equation 1, we obtain 2 times the quantity lambda mu minus lambda prime mu prime times the quantity 2 times x squared minus yz plus the expression lambda mu times the quantity lambda prime plus mu prime minus lambda prime mu prime times the quantity lambda plus mu, that expression times y squared, plus the expression with the quantity lambda plus mu minus the quantity lambda prime plus mu prime, that expression times z squared equals 0. as the equation of the conic capital sigma circumscribed to the two quadrilaterals circumscribed to S. Now the pairs of points lowercase a lowercase b and a prime b prime determine on capital A capital B an involution, the parameters of which are defined by alpha lambda mu plus beta times the quantity lambda plus mu plus gamma equal to 0, and also alpha lambda prime mu prime plus beta times the quantity lambda prime plus mu prime plus gamma equal to 0, which gives for the equation of capital sigma equals 2 times beta times the quantity 2x squared minus yz minus gamma times y squared minus alpha times z squared equals 0, which shows that capital sigma depends solely on the involution on capital A capital B. 3. Let C and D be the double points of the involution just considered on AB. They clearly determine entirely the position of capital sigma with respect to S, and if E is one of the points of intersection of OC and the conic S, then the whole system is projectively determined by the 4 points O, A, B, E, and the cross ratio A, B, C, D. Hence, projectively, there are infinity to the power of 1 systems, such as that formed by S and capital sigma. Since there are projectively infinity to the power of 2 systems of 2 conics, there must be one relation between the invariants of the system S capital sigma. Effectively, if D is the discriminant of S plus rho capital sigma equal to 0, we have D equals rho cubed delta sub 1 plus theta sub 1 rho squared plus theta sub 2 rho plus delta sub 2, which equals negative the expression 1/4 rho cubed plus 2 beta rho squared plus the quantity 5 beta squared minus alpha gamma times rho plus 4 beta times the quantity beta squared minus alpha gamma, with delta sub 1 and delta sub 2 being the discriminants of S and capital sigma, and theta sub 1, theta sub 2 their relative invariants. Identifying, we get delta sub 1 equals negative 1/4, theta sub 1 equals negative 2 beta, delta sub 2 equals negative 4 beta times the quantity beta squared minus alpha gamma, and theta sub 2 equals negative the quantity 5 beta squared minus alpha gamma. As these 4 form a complete invariant system of 2 conics, and only 3 of them contain beta and alpha gamma, by eliminating these 2 parameters we can obtain one and only one relation. We have 4 theta sub 2 delta sub 1 equals 5 beta squared minus alpha gamma, which equals 5/4 theta sub 1 squared minus alpha gamma, and also the fraction 8 delta sub 2 delta sub 1 squared over theta sub 1 equals beta squared minus alpha gamma, which equals theta sub 1 squared minus alpha gamma. Hence, the relation desired is theta sub 1 cubed minus 4 times delta sub 1, theta sub 1, theta sub 2, plus 8 delta sub 2, delta sub 1 squared equals 0, expressing the condition that there exists a quadrilateral circumscribed to S and inscribed to gamma. If we put the cross ratio capital ABCD equals lowercase sigma, then lowercase sigma equals m1 over m2, m1 and m2 being the roots of negative alpha m squared plus 2 beta m plus gamma equals 0. Hence, lowercase sigma is given by the equation alpha gamma over 4 beta squared times the quantity sigma plus 1 squared minus sigma equals 0. And if j equal to the fraction delta sub 1 delta sub 2 over theta sub 1 theta sub 2 is the absolute invariant of the system, then lowercase sigma squared plus 2 times the fraction 14j minus 3 over 10j minus 1 times lowercase sigma plus 1 equal to 0. 4. The second proposition can be stated thus. If the tangents at 3 of the common points of a conic and a triangle go through the opposite vertices, then the triangle is self-polar with respect to the conic. Footnote: transforming quadratically with respect to the triangle, we obtain this. If a rational quartic has more than 3 Fleck nodes, it has necessarily 3 bifleck nodes. For proofs, see Bassett, Treatise on Cubic and Quartic Curves, page 111, and J. E. Rowe, A Complete System of Invariants of the Rational Quartic, Transactions of the American Mathematical Society, volume 12, page 309. End footnote. There are 2 possible cases according as the 3 points are or are not on different sides. In the first case, let ABC be a triangle. A1, A2, B1, B2, C1, C2, its intersections with a conic S. The tangents at A1, B1, C1 going respectively through the vertices A, B, C. Let D be the intersection of B, B1 and C, C1, and E and F the points where B1, C1 meets BC and AD respectively. We have the cross ratio EF C1, B1 equal to -1, and hence AD is polar of E with respect to S. Hence the polar of A goes through E, and as it goes also through A1, it must be EA1 or BC. Similarly for B and C, which proves the proposition in this case. In the second case, suppose that S is tangent to BB1, BB2, CC1. Then B is pole of AC, and therefore the polar of lowercase c going through B and C1 must be BC1 or AB. Since C and B are poles of the opposite sides, the proposition is true in this case too. 5. Another proof will be given here. The system formed by a triangle and an arbitrary conic depends upon 3 absolute invariants, for it is a degenerate quintic with 9 double points, and since the most general curve of the 5th order depends upon 12 absolute invariants, between which each new double point establishes a relation, the truth of our statement follows. Otherwise, also, it is easily shown that the system is projectively completely defined by the 3 cross ratios A, B, C1, C2, B, C, A1, A2, and C, A, B1, B2. That there is no relation between them is seen thus. To any 4 points, A1, A2, B1, B2, taken arbitrarily on the proper sides, there corresponds a pencil of conics which determines on AB an involution, a pair of which will be defined in one of 2 ways by the cross ratio AB C1 C2, which is thus shown to be arbitrary when the other 2 cross ratios are given. Now if we impose upon the system the conditions that 1 or 2 of the tangents to the conic from the vertices meet it on the sides, they alone will do so, and the conditions are independent. For there is a conic tangent to AA1 in A1 going through B, and a tangent to an arbitrary line at its intersection with AB, and for this conic AA1 is the only tangent from the vertices meeting it on the sides. Next, among the conics tangent to AA1 in A1 and to B1 in B1, there is one tangent to AB at a certain point K, with respect to which B1K and A1K will be the polars of A and B, and therefore again AA1 and BB1 are the only tangents from the vertices which will meet this conic on the sides. The same is evident for conics tangent to AA1 and AA2 in A1 and A2, since for them AB and AC are arbitrary. If now we impose upon a conic the conditions that three of the tangents at the intersections with the sides of the triangle go through the opposite vertices, these conditions being projective and independent will determine the cross ratios on the sides. Hence any two systems satisfying these conditions for which the cross ratios are definite will be projectively equivalent. But such a system is presented by a conic and any one of its self-polar triangles, into which the system considered can therefore be projected, and this proves the proposition. Lincoln, Nebraska, November 28, 1911. End of Two Theorems on Conics by S. Lefschetz. Recording by Prachi Pense, Wilmington, Delaware.